Hello, everyone, and welcome to the latest episode of Scrubbing the Skies, the webinar series of the Institute for Carbon Removal, Law and Policy at American University. As always, I'm your host, Will Burns, and I serve as the co-director of the Institute. So let's move now to today's program. The website CDR FYI documents that the vast majority of carbon removal purchases to date have been for biochar. However, beyond the fact that virtually none of these projects have delivered yet, the aggregate promised amounts are also extremely modest in comparison to the billions of tons of CO2 that ultimately must be removed by the middle of the century and beyond. Today's speaker, Cameron Roberts, a postdoctoral researcher at the University of Wisconsin, is the lead author of a recent paper in the journal Technological Forecasting and Social Change that seeks to address the question of how we might substantially scale biochar to help us get to the promised land. The study draws upon historical lessons learned from a number of other sectors and their potential application to biochar. I found it a useful and helpful set of data points as we move hopefully from biochar as largely a notional concept to a potentially important component of a CDR portfolio. So we'll start with an initial summary of the study by Cameron, and then we'll move on to the Q&A session. So please start populating the Q&A box during the presentation. Cameron, welcome to the show, and the floor is yours.
Great, thank you very much. Can everybody see me and hear me okay? Okay, I will just share my screen. Can everybody see it? It should be just the slide. Yeah, looks good. Okay, great. So, thank you, Will, for the introduction, and thank you for the invitation. I think you're right in how you've positioned this as an issue of taking this from a notional concept into something that is scaled and is a real industry in the world. That's what we're talking about. We're talking about growing a new industry from scratch, and that's most carbon dioxide removal. And there's a lot we can learn about from in history for that kind of thing, how we grow industries. So yeah, the title is The Upscaling Biochar as a Soil Amendment and a Waste Management Technology, Lessons from Agricultural History. This is sponsored by the GENI, the Geoengineering and Negative Emission Pathways in Europe project, which is an ERC-funded project, and I'm at the University of Wisconsin-Madison. And I should credit my co-authors as well, Jenna Green and Greg Nemeth, as helping with this. So I have a brief introductory anecdote. This is a very poor quality digital scan of a German woodcut from the late 19th century, illustrating something called Brandkultur. I'm sure I'm pronouncing that wrong, but the general idea is that on high German hills in the Black Forest, I think places like that, you would burn hillsides to release nutrients. You would then use those nutrients to farm for a season or two. You'd move on to a different section of the hillside, burn that, eventually come back to where you started after some more vegetation had grown. It worked pretty well. It was generally a kind of poor marginal form of farming, but it worked with people who practiced it. The people it didn't work for were the people in the valleys below, in the towns, whose towns got filled with smoke every spring. These were wealthier people than the hill farmers, and they complained to the government. Fortunately for the government, there was an alternative in the form of potash fertilizer. Germany had just discovered a mother lode, and in fact, the world's first mother lode of mineable potash. And so the national government tried to suppress Brandkultur. They put various regulations and bans on it. They encouraged the uptake of artificial fertilizers. The Coles Notes version of this is that it did not work. It was too expensive for the farmers. It was too big of a change in their established practices. They kept burning hillsides for several decades, going into the era of the World Wars. This is comparable to biochar in that we have a social problem, which is solvable with a change in farming practice, and effectively a way to kill two birds or multiple birds with one stone. But the story shows that the system doesn't necessarily behave rationally, nor does it respond to policy incentives. It has its own inertia, it has its own culture, it has its own entrenchments in existing ways of doing things. And that's what you run into a lot with biochar, and that's what I'll get into in a bit of a broader picture in a minute. However, first I'm going to give a brief outline of the presentation. I'm going to give a brief introduction to biochar. I'm going to talk about three historical analogues for biochar. One is fertilizer, another one is ethanol, and then the third is compost. Then there'll be a discussion, conclusion, and some policy implications for biochar. So to introduce biochar, I'm going to assume that this is a pretty switched on audience and that you generally know what biochar is and how it works, but I'll briefly go over the basics. The general idea for biochar is that you take biomass, usually plant biomass. It could be agricultural waste, could be forestry waste, fishery waste, and you pyrolyze it, which means you treat it at very high temperature with no oxygen. This turns it into what is essentially chemically pretty similar to charcoal, except instead of burning it as charcoal, which is a solid form of carbon, except rather than burning it, which is what you do with charcoal, which releases the CO2 back into the atmosphere, you instead put it somewhere durable, where it's going to not get burned. The most common suggestion is soil. And the reason to put it in soil is that it has some agricultural benefits, which I'll get into in a second. So the carbon sequestration potential of this ranges from 1.1 to 1.3 gigatons per year, potentially up to 10% of the required carbon removal for the 1.5 degree pathway. And if we have dedicated biochar crops, so we're growing stuff like switchgrass purely for the sake of pyrolising it, making biochar, could be up to 35%. It also offers a side benefit, gives us a way to dispose of some challenging organic wastes which cause pollution currently when they're disposed of, and it produces low-grade heat as a byproduct, which can sometimes be used for things like space heating. And it has a range of uses. So I've already talked to about agriculture. That's what I'm mostly going to focus on today. But for the sake of completeness, I also have to mention it can be used in construction. It is quite useful as a concrete additive, environmental remediation, and some other industrial uses. There is very strong historical precedent, in fact, prehistoric precedent, for the introduction of biochar to soils. This is a picture of something called terra preta, which is found in the Amazon basin and areas near there. The indigenous people there would add charcoal to the soil. And this is some of the most fertile soil in the world for that reason. Studies on biochar have found that it has benefits on water retention because of its porosity. It's like a sponge, it absorbs water and releases it slowly. It resists soil compaction. This is a little more scientifically controversial, but there's good evidence that it can provide habitats for beneficial microbes. In some cases, it may have essential nutrients for plants bound up in it, so it can fertilize the soil. And it can provide additional carbon sequestration in addition to the carbon in the biochar itself through the effects it has on soil biology. There are studies that the studies are pretty solid that it improves agricultural yields when you add biochar to the soil. The wrinkle, however, is how you weigh the value of those yield increases versus the cost of the biochar itself. And unfortunately, thus far, the biochar is more expensive than the yield increases you get in most cases, and this has been a major barrier. There's also some issues. There's a lack of best practices. It's a very complex product. Every kind of feedstock that you can potentially use, going through different kinds of pyrolysis processes at different temperatures, water, no water, etc., can then be specialized for different kinds of applications, different kinds of crops, in different kinds of conditions. So it's very complex, and there's a lot more that needs to be done on that. And also the collection of feedstocks is very challenging. When you're thinking about agricultural waste, forestry waste, things like that, they're spread out over a very large area, and we don't have infrastructures to collect them. A process which is known as reverse logistics, which can be very, very hard to do. So essentially, there's three subsystems that we need to address, that big changes need to happen in. First, the feedstock subsystem. We need to collect or produce a sufficient quantity of biomass to be made into biochar. This is essentially a change in the waste management system and requires new incentives in that. Second, we have a processing subsystem. We need to build pyrolysis facilities, some of which could be quite expensive. And this involves large sunk investments, There's also a bit of an innovation gap. And then third, the application subsystem. We need to get farmers to actually use the stuff. For the record, I'm only going to talk about farmers from this point on. The construction side of things, other uses would benefit from similar studies, but I had to draw my boundaries somewhere. So you have to get farmers to use the stuff. You have to physically distribute it to them. You need to persuade them to use it. You need to finance it somehow, and you need to establish best practices. The common story you hear from proponents of biochar is, and indeed critics of it as well, this is the kind of most plausible story that gets told, is that carbon credits are kind of the secret sauce that makes all of this work, right? You through carbon pricing or through voluntary carbon offsets or something like that, you can bring money into all of these steps, and that facilitates everything. The loggers selling timber offcuts get some money. The pyrolysis people get some money. The farmers get some money. Who gets how much money? How big each of these arrows is of course a slightly controversial point, and a problematic thing going forward. But this is the idea that this is we'll use carbon credits to create the right financial incentives, and that'll basically solve the problem. So to study these three areas, I used a methodology that I developed in partnership with Greg Nemeth, who works here with me, called the SHARD methodology. This is systematic, historical, analog research for decision making is the acronym. I'm not going to go into every detail here, but I do invite people to. I'm happy to go into it in more detail in the question period if people want to hear more. More or less, this is a method for using accountable and repeatable and transparent approach to choose a historical analog for what we call a target innovation, a present-day technology, which in this case is biochar, and to analyze it to systematically draw conclusions. It's meant to deal with the issue of how when historical analogs are used, the typical criticism that comes up is, well, you could have chosen any analog, you chose the one that fits your conclusions, right? So we're trying to be a bit transparent about this to get around that. So in the case of biochar, we identified some possible analogs from a number of sectors, and we sorted them according to whether they apply to feedstocks, processing, or application, including for purpose-grown crops versus wastes, and as a soil amendment versus for industrial or other uses. And we identified the scale of the industry, but from mostly experimental to a global massive industry. And we found a few that are particularly good analogs. So fertilizer, so virtually everything involves some kind of processing. So that's an easy box to tick. The question is something that involves both biomass feedstocks, including both waste feedstocks and purpose-grown crops, and is used as a soil amendment. The only thing that we could find that ticks all three boxes is compost. But that's a relatively small industry compared to the scale that biochar might need to be. And so we also introduced some partial analogs that cover two of the three. So one is just fertilizer, nitrogen, phosphorus, and potassium, which is a giant global industry involving both processing and soil application. And then the other one is ethanol we focused on as a larger industry connecting feedstocks to a processing system. So that's how we chose our analogs, and that brings me into discussing the analogs themselves. So I have to apologize in advance. These histories are going to be very, very short. It's not easy to cover the scale of time that we're talking about here, particularly and the number of countries for three different historical processes in the presentation of this length. But I'm happy to go into more detail about things if people would like. So fertilizer dates back scientifically to the 1840s when Justus von Liebig just figured out that you could actually just give elements to plants in a pure chemical form and they would absorb them just fine. This led fairly quickly to the development of a soil amendment industry, which depended heavily for a while on Peruvian guano, in particular for nitrogen and phosphorus. Phosphate salts or nitrate salts in the Chilean desert also played a role. Mineable potash in Germany, discovered in 1856. 1913, the Haber-Bosch process first allows us to fix nitrogen directly from the atmosphere. And then from the 1950s onwards, there's a rapid global transition to modern agriculture, which goes along with massive adoption of fertilizer in countries around the world. You'll notice that this is more than a century after the first discovery of this, and the better part of a century from the earliest development of an industry, which shows how long the time lag on this stuff can be. To go into a bit more detail, I'm going to talk about 3 countries. So going back to Germany, synthetic fertilizers started to become available in the 1830s. Obviously, 1840s is when the value first got recognized. And this was available as a byproduct of the coal industry. There, around the turn of the 20th century, there was a desire to increase agricultural yields, and a kind of scientific industrial complex with heavy state supports started to heavily promote fertilizer use. Some farmers were reluctant to apply it. Some over-applied it because it was easier and less risky to over-apply than it was to follow exactly the scientific advice. Then there was a kind of agricultural crisis in the First World War, leading to very, very heavy fertilizer use to make ends meet agriculturally, because their food imports had been largely shut down. At the end of the war, there was a flooding of the market with ammonia due to the upscaling of nitrate production during the war to produce munitions, which led to a gradual increase in fertilizer use. And then in the 1960s, in the Cold War context, there was a kind of modernization frenzy where modern agriculture was expanded rapidly. In the United States, a lot of the story happens in the South. Much of American agriculture in the 19th century didn't need fertilizer because there was so much land and labor available. There were ways of maintaining soil fertility that were much cheaper and more secure for individual farmers, and didn't put them in debt in the way that fertilizer tended to. That changed in the South at the end of the Civil War, because the system of soil fertility maintenance at that time depended heavily on enslaved labor, and had also been damaged by the war itself. And so some southern states following the Civil War became world leaders in fertilizer application and the development of fertilizing, of best practices. First World War sees, similar to Germany, a flurry of experimentation with fertilizer production to supplement for imports that had been lost. And once again, end of the Second World War in this case sees a huge nitrate surplus because they were producing munitions for the war. This combined in the 1950s with the Midwest that had began growing hybrid corn, which demanded enormous amounts of fertilizer. And this was combined with growth in soil testing, bulk blending, agricultural advice. This led to a rapid increase in fertilizer use. Finally, in China. So the big story here is famine and food shortage in the 1950s going into 1960s, followed by the opening of the Chinese markets in the mid-1960s, when China purchased 5 very large ammonia plants from the UK and Netherlands. This was the largest industrial purchase ever of its type. The Chinese authorities began taking a strong interest in modernizing agriculture, as population growth was putting pressure on traditional methods. And within a decade, China surpassed the USA in nitrogen fertilizer consumption. Within another decade, they surpassed the USSR in fertilizer production. So very rapid kind of state-led growth. So when we look at patterns in this, I've created this kind of Venn diagram here. We find a few things that show up: crisis, need for an urgent need for farmers to produce more, rather than just a kind of incentive that they can make a profit by producing more. Supply side factors, so important knowledge and innovation support, such as universities, extension schemes. An increase, a large surplus in provision of fertilizer, and financial support, such as loans and falling prices. This was weighed against economic constraints, quality control issues, resistance from farmers, and mismatch with existing farming practices. Um, so moving on to ethanol. So this is a picture of one of the first American ethanol gas stations, which you'll notice looks a lot older than the 1970s, which is where the story often starts when you hear the story of American ethanol. This is in the 1930s in Nebraska. And there was a brief period there when farmers, due to a corn surplus, began making it into fuel, and there was a regional industry in it. Um, but the industry goes back much deeper, has much deeper roots in Brazil. Um, the Brazilian government has supported the sugarcane industry for various political and economic reasons since the late 19th century. And this led to sugarcane ethanol having a fairly long history, playing a role, for example, as a wartime fuel during the First World War when Brazilian imports were restricted by the war. The Brazilian government, as early as 1933, were providing innovation support from the Institute for Sugar and Alcohol. In the Second World War, there was another fuel shortage and a disruption of sugar exports, which led to more desire to support ethanol, and which meant that by 1970, the ground had largely already been laid. Going into 1973, two things happened: an oil crisis and an international sugar price collapse. This led the government to establish the Pro-Álcool program, which involves subsidies, compulsory blending standards. So in Brazil, all gasoline must be blended to, I think, at least 10% with ethanol. State support for production, promotion of flex fuel vehicles. This stuff, the flex fuel vehicles are the latest thing that goes into the kind of early 2000s. In the United States, there is a similar story with slightly different policy levers being used. So 1930s, as I mentioned, falling corn prices encouraged some adoption of ethanol. But it was the 1970 oil crisis which once again played the key role. There was also concern about lead in fuel in the United States, and ethanol works well as a substitute for lead, as an anti-knocking agent. So that played a role as well. 1978, the Energy Tax Act established a tax exemption for ethanol. Subsequent legislation continues to provide incentives, this has remarkable policy stability going through the later 20th century, including, for example, during the Reagan years when there was a very large skepticism against these kinds of programs. The 90s, when low gasoline prices and high corn prices put a lot of pressure on the industry, but policymakers redoubled their support. So the patterns we see here is state support, which involves economic, blending standards, subsidies, etc., but also systemic, such as research funding, support for flex fuel vehicles. Export and energy crises played a key role, a glut in some key agricultural commodity, some role of innovation, political incentives, and side benefits, pollution abatement and engine performance enhancement played a role. So what we see here is the political economy aspect of it is very strong. You have this situation where it provides security to the energy system and revenue to the agricultural system, and it's specifically countries that have large sugar-heavy agricultural exports plus issues with energy security that do this, right? The U.S. and Brazil both ticks both those boxes. So my final example is compost, which is notable in its comparison with biochar, that it turns biomass into a soil amendment. Compost has been used since prehistoric times, but it was precisely that fertilizer revolution I mentioned earlier, which separated processes of waste management from processes of soil amendment. There was some pushback in the other direction in the 1930s, largely ideologically motivated. And then it was Albert Howard, who was a British soil researcher, invented the indoor process. But there were very few takers initially. One niche for it was in the Netherlands when land reclamation used heavy amounts of compost, and so there was a government agency that pushed the development of the composting industry there and developed a lot of best practices. But it was really the 1960s when the environmental movement led to environmental movement plus the consolidation of farming created a niche for organic farming, and at the same time, consumer concerns about organic or about fertilizer-heavy agriculture led to a market for this. And this was boosted by some legitimation of the organic movement in the 1990s to 2000s. New waste management rules created new organic waste streams. So, for example, lawn clippings were banned in landfill in some places, which meant you had to find somewhere else to send it. Households became more willing to sort their waste. Technical improvements led to higher quality compost. Eventually, there started to be a more solid market for this. So the patterns here, I want to point this out. This is a gadget you can buy, which costs $400. And it's essentially a countertop compost maker that heats it up and makes it. So this is a machine that makes dirt, and you can pay $400 to have it. I think that illustrates the extent to which compost has benefited from a sort of cultural cachet. And that played an important role here. But there was also issues of a waste management crisis, concerns about a lack of landfill space, new practices of waste handling, small, heavily ideologically driven experimentation. Perhaps we could see this thing as oh wait, I'm sorry, I'm looking at the wrong slide here. I'm sorry about that. This is where we should be, right? So yeah, this thing is what I'm pointing to. This Lomi gadget. Um, yeah, new practices of waste handling, small ideologically driven experimentation, niche applications, and then the importance of organic agriculture as a social movement. I think is really big. So I know I'm a bit over time, but I'm going to illustrate a few major points here. So these are things that show up in every in both cases or all three cases for processing that apply to feedstocks processing or application. So feedstock surpluses, a glut, or a bonanza would be another way to phrase it in some cases, shows up in both cases. We don't currently have this for biochar. They don't pose a waste management problem. In fact, gathering them is an issue. In the processing side, to spur investments in the production facilities, you need either reliable markets or institutional support. The fertilizer industry struggled when demand was low. Ethanol required subsidies and blending standards to reassure producers that people would be buying it. Compost, there was very limited investment before the organic movement. Biochar has a similar chicken and egg problem. And then for application, the role of systemic agricultural change, whether we're talking about the modern agricultural modernization or the kind of the counter trend of the organic movement. The point being that these were popularized in the midst of larger changes to farm systems. Finally, quality assurance. For fertilizer, fraud was a big problem, and that was a big thing that the fertilizer extension schemes and things like that had to deal with. Biochar might also have similar risks. A few minor points which are less well illustrated, but I think are worth thinking about. The political power of producers is a huge part of the ethanol story, and we might want to think about what that looks like for biochar. On the application side, quality assurance is sorry, I put that in. That was a mistake. Put that in repeated. That's a repeat. But agricultural crisis was a major factor in the transition to fertilizer-heavy agriculture. It was not done typically as a result of farmers just realizing they can make more money. Often they were just forced to do it by one thing or another. And then the consumer willingness to pay to offset it. And I wonder, does that mean we could have like a certified carbon negative food product? I see Will has turned his camera back on, so I know my time is limited here, but just going to the conclusion. The standard story is that biochar is supposedly a win-win-win. You get waste management, you get agricultural productivity, and you get carbon drawdown. So everybody wins. Carbon credits help make the ends meet. This suggests a kind of agricola economicus, like Homo economicus, a farm and a waste management system that responds rationally to incentives, and a rational kind of cockpit model policy system, which is in a deliberative fashion pursuing this goal. But the history of changes in these sectors shows a lot of other factors at play. I've already talked about them a lot. I'm not going to list them, but you can read the list there. So the point being, don't expect biochar to succeed based on the strength of its business or policy case alone. A real transformation will be messier, and intervening in that messiness is going to be an important part of how we can make it work. So thank you. That's the end of my. I'm sorry I went over a little bit, but I'm happy to take your questions in a moment.
All right. No, you're just on time. That's fine, Cameron. So thank you very much for that. Yes. So please start populating the Q&A box with any questions that you have, and I'll try to seed that with a few questions of my own at the outset. Uh, One of the things that you said, Cameron, toward the end is that we'll probably have to create some incentives to drive this system. That it's not going to happen purely by the serendipitous machinations of the market. If you were thinking of a singular or a couple of government policies that you think might be most impactful in terms of helping to scale biochar at this point, what would that be?
I think probably the best thing would be a stronger use of agricultural extension schemes to possibly as a kind of agricultural extension schemes have been eroded a little bit since their peak in the kind of 1930s into the 1970s. But that's a system and for those who are not familiar with the concept, this is a system wherein the government, sometimes the academic sector is involved. The University of Wisconsin-Madison is involved in some of this, operates advice services, operates regional or local agricultural laboratories, experimental farms, things like that, to develop best practices for farmers, to advise them on these best practices, to help them use science to improve their process. Biochar is scientifically complicated, and I don't blame farmers for being a bit mystified by it, even the ones who might be interested. They're going to need not only help, not only advice, but that advice has to be tailor made for specific contexts, for what crop you're growing, where you're growing it, what kind of biochar is available there, what the climate conditions are, what the soil conditions are. And that's going to mean a lot of small research and extension facilities in local areas to experiment with this, along with other possibly carbon negative or low carbon agricultural techniques. I do think making this as a part of a package of a larger package of agricultural innovations for climate change is probably a good idea. But yeah, I think government funding and academic involvement with a system like that does sort of a network of scientific infrastructure to help farmers directly so they can figure out what to do and they're not just on their own is probably the best thing we could do.
Do you think among the albeit limited, as you pointed out, cadre of agricultural extension people that we have out there, that we have a sufficient number of them with expertise in biochar to make that realistically happen?
Probably not. It would probably require some recruitment. I know there's, I mean, I am a social science scientist of innovation, so I'm not an agronomist. But I can imagine someone in my career position, postdoctoral researcher, with academic expertise in this kind of thing. That could sound like a pretty good job. I think you could build up this workforce, but yes, it would take time, and would take investment, and it's not something that could be done just with a kind of a sort of a single high leverage policy incentive or something like that. It would require building a system, which is hard.
Yeah, I think that's true. So let me ask you one other question, and then we'll move to some of the audience questions. One of the things that you said again toward the end was that ethanol benefited from developing a powerful kind of political constituency, and I can see why that can be beneficial in terms of scaling up an industry. But we also know the history of ethanol arguably are powerful constituencies pushing for a process that ultimately may not have turned out to be very desirable from an economic or environmental perspective. And so I wonder, how do we give the biochar industry some political heft, but avoid some of the pitfalls of having a vested interest drive a process in a way that may not have been totally scientifically sound?
Yeah, I think that's actually a huge problem with biochar and really and a lot of carbon dioxide removal, and in some ways a kind of fundamental criticism of the entire idea. I don't think that it disqualifies it, but I don't necessarily have easy answers either. With ethanol, I think people make a mistake in characterizing ethanol as an environmental innovation or an environmental set of policy measures. Ethanol was an energy and agriculture and farm economics innovation, um, and and existed for that reason. And the environmental story was for the mostly just an additional political justification for it. But it was not where the real power came from. And I think this is a problem you get in general with climate change in general, is that the environment has no political voice. Um, the best it can do is have human political actors who care about it. But the problem is that then comes from that usually doesn't connect directly to their livelihoods in the same way that, say, a farmer will assert their interests, right? If to brainstorm possible solutions to it, I mean, I I think having a strong building up a strong scientific infrastructure, as kind of scientific slash legal infrastructure, as early on as possible, preferably like now, to adjudicate the question of how much carbon is being sequestered by X amount of biochar when you put it, and for how long. Um, because that's a question that people are going, as soon as this becomes a profitable industry, people are absolutely going to try and fudge the numbers on that to make more money, and they will hire lawyers and lobbyists to help them do that. Um, and so the earlier we can have a kind of neutral, objective institution that handles this, that is respected by all parties, the better. And that's easier to develop when there's less money at stake. Um, and so that's the best I can offer. But honestly, I think it's a really hard question that I don't think anyone has a compelling answer to just yet.
Yeah, no, I think that's a good answer. I think that moving away from the Wild West that seems to be attendant to the voluntary carbon markets, and having government standards is going to be beneficial for everyone. It doesn't necessarily stop vested interest from capturing government, right? As we saw, I think arguably in terms of ethanol, but I think it gives us a fighting chance. So let me move on to the questions that we have here. Here's one. It's a comment and then a question. It says, like usual, the U.S. is still 10 years ahead of Europe. But what has limited the upscaling of biochar? Is it the availability of biomass being especially scarce in the United States?
Um, that is that is the perhaps the original cause. The more proximate cause is that it's expensive. That's ultimately what it comes down to. It doesn't justify the yield increases that you get. It's not so much that biomass is limited. There's plenty of biomass, of waste biomass, that just gets burned. For example, the ethanol industry itself produces enormous amount, and the corn industry, for the corn that you eat, that livestock eats, produces enormous amounts of waste corn cobs that are all in big piles at processing facilities. This is an ideal feedstock for biochar, but it just gets burned. There's no infrastructure to collect it, to pyrolyze it. Um, and uh, and because of that, because the logistics haven't been established to take those feedstocks and process them, biochar remains quite expensive. It's also competing with charcoal which is purchased as a fuel and already has an established market price for market share. And so a farmer trying to buy biochar is competing with someone with a backyard grill trying to buy a charcoal effectively. And So there's a lot of reasons why it's expensive, but yes, I think the cost is the biggest one, and then the other one is the fact that there's not so much awareness of it, and there's not a lot of best practices. If you're a farmer who wants to use biochar, who maybe is even willing to lose a bit of money to for the sake of experimenting with it, um, is you have to you have to be reading. Like, no one can give you a straight answer about what is the best way to use it. um, and and that is, yeah, that makes it really hard for them to adopt it. So that speaks back to the extension services point that I raised earlier.
Hmm. Yeah. And do you have a sense? I mean, one of the things that you said in the piece was that uh, the potential increased agricultural yields associated with biochar would not be sufficient to offset the cost of biochar for farmers. Do you have any sense of what that spread is? How much would we have to bring down the cost realistically for farmers to have an economic incentive, or at least end up uh, cost neutral in adopting biochar at this point?
Yeah, I can't put a number on that. I have read some papers that do so. I believe some of them are cited in my art in our article. So if people want to look that up, that might be a starting point. There's one called The Glory and Misery of Biochar that talks about this in some detail, although it's a little bit outdated. But what I have heard is that it is a gap that is bridgeable with carbon pricing that is within contemplation, right? So I think it's like I think $100 a ton, possibly less, of carbon price would bridge the gap. And so that gives you some idea of where that might lie. But yeah, I'm not confident enough to put a specific number on it.
Yeah. Yeah, it's a really important question, right? Ultimately, that you mentioned other potential avenues for purchase, but I think agriculture is going to end up being the lion's share, right? And ultimately making that economic model, whether it's increased crop yields or sales of carbon credits, right, or a combination thereof, right, is going to end up being a critical consideration. So to be continued. Um, Another question. Can you clarify what the benefits are to turning feedstocks into biochar rather than compost?
Um, yeah, so I'm not an agronomist, and an agronomist would be able to speak about this with more authority. Um, I do know biochar sequesters carbon in a way that compost does not. Um, Compost can be degraded by microbes which then exhale carbon dioxide. In fact, that's partly the point, right? You want it to be taken up as a nutrient by plants and by other things living in the soil. Biochar is The whole point is that it's chemically inert. It's not chemically inert, but it's biologically inert. There's not a lot that can eat pure elemental carbon. So it, instead of being nutrition and nutrients, although it may have some trace nutrients in it, what it provides more is habitat and structure um, for for organisms in the soil, and therefore it does not get consumed, or if it does get consumed, it gets consumed over very long time scales. And that is why biochar provides a negative carbon, it is a form of carbon dioxide removal, whereas compost generally is not. But they serve from a farmer's point of view, they serve fundamentally different purposes. You get some compost is for fertilization. Biochar gives you some marginal fertilization, maybe depending on the biochar. But it's more for like physical properties of the soil is what the reason you apply it.
Okay. Next question. Do you believe that biochar, I think biochar uptake might move faster in Africa, where fertilizer can often not be afforded, and biochar can be made while cooking.
Um, yeah, so I can imagine how you might make biochar while cooking. A pyrolising stove. I haven't heard anything about that, but if the questioner has heard about that, I'd love to, if they have a link to a paper or anything, that sounds really cool. Um, so one interesting thing about biochar is that it can be made in any kind of facility from literally a pile of dirt. That's how they made it in the Middle Ages, right? Or more often today, it's a steel, an old rusty steel barrel is the very low tech method, all the way up to a giant mechanized, technically sophisticated co-firing system that uses the heat for district heating and precisely tailors the temperature to produce optimal quality biochar, et cetera, right? And there's some of that being built in Europe right now. Um, so and also the smaller things can sometimes be mobile. There are people experimenting with mobile pyrolyzing units. Um, so I I don't I think there could, I can see the logic to what the questioner is saying, that in rural contexts, in developing contexts, in poor contexts, um, there is an opportunity here to possibly turn a waste product into something that is useful locally and can augment soil and improve yields, or that is or that can be sold into a larger market. So I I think there is certainly a case to be made for it. I think in many developing country contexts, that is, it'll be a system that looks very, very different and probably will produce biochar of more variable quality, which will possibly be a challenge for its use as a soil amendment, at least in the way that it's being discussed in many cases. But that's the biggest obstacle I could think of. Otherwise, it sounds like a pretty good plan.
Yeah, I'm curious, related to that, in the instances that you were looking at, in terms of other historical examples, were any of those ones where there was a major component in the global South, or were these mostly developed country initiatives?
Oh, well, certainly fertilizer. Um, and well, yeah, fertilizer is the big one, and the whole story of the Green Revolution, right? And I read the histories of fertilizer in many countries around the world, and including many global South countries, and very often the story of fertilizer being adopted in those countries was a story of some kind of political or societal or economic crisis. Either farmers were pushed into new kinds of debt that been they hadn't been pushed into before, and therefore they couldn't just do subsistence farming anymore. They needed to produce a profit, and therefore they had to increase their yields. Therefore, they needed fertilizer, which put them into more debt. Um, or there was a population growth or a kind of strip mining of the soil through over intensification, things like that, that suddenly created a need for farmers to produce more, either for their own needs to make more money to service oh, their own financial obligations, or for societal needs because the society had a food crisis. Um, and yeah, that's a huge part of the story. And it's some of the best illustrations of the fact that this was not a story of farmers just sort of looking at a spreadsheet, or the equivalent of a spreadsheet at the time, and saying, "Oh, hey, look, if we add fertilizer, it'll cost me this much, but I will get this much extra yield, and therefore I'll make this much profit. Therefore, I should do it." Historically, farmers don't appear to have made that kind of calculation for something as fundamental as a transition to fertilizer. Instead, it was a result of them being pushed into it by something or other, or a result of a much larger systemic change that they could then just roll the fertilizer into.
Yeah, I think that's an interesting conclusion. Um, Next question. Can a biochar facility be constructed in any climate?
Yes, to my knowledge, yes. So essentially, all you need to do to produce biochar is you need to have some kind of biomass feedstock, which could be anything. It's you need a vessel which you seal off from oxygen, and then you need to heat that vessel, which you can do through you can do just using a wood fire underneath it. So it's yeah, it can be done virtually anywhere. The thing that is geographically specific about it is what kinds of feedstocks you have access to, because different kinds of agricultural sectors or natural resource sectors will produce different kinds of organic waste. Um, and that will and that will produce biochar of different quality. And I don't mean quality purely in the sense of good or bad. I mean quality in the sense of like what it looks like under a microscope. It's just qualitatively different. Um, and different kinds of biochar with different kinds of properties are good for different kinds of applications. So the critical question is, can you match up the biochar that you can produce where you are with the kinds of applications that are in demand close to where you are within a reasonable shipping distance? Um, and that is, I don't know if anyone's done any big systemic analysis of that yet, but it is something that might be disqualifying in some cases, that you can't make the right kind of biochar.
Yeah, I think the mapping process is really important, and again adds yet another layer of complexity, right, to the calculus, right, and again argues in a need to train up a lot more extension folks to be able to do some of that characterization. Um,
Yeah, and
yeah,
if I can elaborate just a little
yeah,
bit more, so for fertilizer, the scientific uncertainty about fertilizer, the thing that a farmer needs a scientist to help them with, is some very simple numerical questions. How much of the nutrient does your crop need? And how much nutrient is in this bag of fertilizer that you just bought? Because once again, there were issues with fraud, right? Um, Biochar, so that's two numbers you need. Biochar has just at least a dozen different properties that can be evaluated in various ways for both the biochar itself and the application environment. So the issues of fraud and best practices and scientific complexity that attended fertilizer use will be multiplied several fold in the case of biochar. And I think that means we should take it very seriously.
okay. Next question. The open kilns seem to facilitate equitable inclusion of farmers in rural and developing country contexts. But can we address the fact that research clearly shows that these systems are not guaranteed to be net negative in their emissions in real world settings? Have any sense of that?
I am not entirely familiar with that research. It does if they're not net negative, I do kind of wonder then, because you have a physical lump of carbon, which you know came from carbon in the atmosphere. That's what biochar is. So that is, as long as you don't burn it or it doesn't degrade in some other way, it's hard. You sort of have a very physical, tangible evidence of at least some level of net negativity. Um, the only question is whether it's degrading in the soil faster than people think it will, which is an issue that is debated a little bit. So I am but possibly there's some aspect of the science I'm missing out on there. Um, I'm I guess I would say that yes, we probably do get the greatest benefit, both in terms of carbon sequestration, in terms of verifiability, monitoring. What's the acronym for that? I forget what it is. Uh, right. And the the quality of the resultant product from a large centralized facility. But then that does lead to a logistical issue or a reverse logistics issue. And it also, yes, is a problem for not just the developing world, even just for cash strapped farmers in the American Midwest, who some of whom are don't have a lot of slack capacity to participate in that kind of a system, right? And uh, so it's whereas yeah, a kind of mobile unit or a small on-farm unit or just a barrel that someone owns could potentially, which they use to heat their home, maybe could potentially be more accessible to a lot of farmers. But then the trade-off is there's quality issues. So that is a trade-off that's going to need to be thought about very carefully.
Yeah, I think it's an interesting question. I don't know that literature well either, but that seems to be a really critical issue for research because I agree. Once you start looking at the carbon footprint of transporting what is a very voluminous thing, large distances, and you look at the cost incentives or lack thereof for farmers, I think that if it's possible to do a lot of this in situ, right, it's going to be a lot more economically viable. But I think there are those life cycle assessment questions, and um, uh, yeah, something to look at. That I haven't seen any of that, but I take the questioner's point.
I
Um,
did notice that they answered what I said about why it would be not net carbon negative, and they noted the energy used to pyrolyze it. Yes, certainly if you're using natural gas, but then natural gas would be more likely to be used at a large central facility for pyrolysis. Pyrolysis is self-sustaining. It's not. It is like a fire in that sense that once you get it to the temperature you need to get it to, it does the reaction does sustain itself. Um, it provides its own heat. However, you do need to get it up to temperature. I think in smaller units, that is typically done with biomass, and often the same biomass that's being used to produce the biochar itself. Um,
right.
so, yeah.
Okay. Okay, well, we have reached the top of the hour, and so I would once again like to thank Cameron for his presentation, and thank everybody for their questions. We will be back next month with a couple of new topics, and I hope many of you can join us again. And until then, thank you, everyone, and goodbye now.
Thanks. Bye.